So one of the big problems we kind of have to do here is calorimetry type problems, and this is the one that requires the most math. It's not hard math. It's the kind of math you've been doing since like 5th grade, but it's a lot of it, and it's a lot of detail, okay? But the properties of distributing multiplication over addition and subtraction, you know, those are things you probably learned in 5th grade, okay? And that's the basic algebra stuff. You've been doing that for a couple of years, so it's not really a lot of new math. It's a lot of it all in one thing, okay? So you got to keep all these orders of operations straight. So here's the problem. If 20 grams of silver at 350 degrees C are mixed with 200 grams of water at 30 degrees C, find the final temperature of the system, and it gives you the specific heat or heat capacity of silver, 0.233 joules per gram per degree C. You have to know from memory the heat capacity of liquid water, 4.18 joules per degree C per gram. That's just expected. Now, what we need, now it might be helpful to you to make a list of what you know and don't know. Okay, I didn't do that, but remember we did that when we were doing gas laws. We made a list of everything that has to do with the beginning set of values for gas and then a list of the ending set of values. So you might do the same thing here, where you list out all the values for the silver and all the values for the water to help you keep everything straight when you set it up. But let's start doing the problem here, okay? So this is a system and surroundings type problem. In the system, whatever is happening to the energy in the system, whatever change there is in the energy in the system has to go to the surroundings. That's the only choice we have, system and surroundings. So remember we looked at this. We got the system, and what we're doing with the calorimetry problem is we're isolating a tiny portion of the universe. In reality, what's happening in the system, whatever change of heat energy there is in the system has to go to the surroundings, or has to be taken from the surroundings, okay? That's all you got. You got system and surroundings, and all together that makes up the universe, okay? So whatever energy leaves the system has to go to the surroundings. Whatever energy leaves the surroundings has to go to the system. That's all you got, those two choices. And that's all we're doing is calculating that. It gets more complex, of course, mathematically, but that's essentially what we are doing. All right, so this is what we're looking at. The energy that's leaving the silver is going to the water. We've isolated a tiny little part of the universe to this little, like it's as if it's completely isolated, completely perfectly insulated from everything else in the universe. It's a mini universe we got here, okay? So whatever energy leaves the silver goes to the water, or vice versa. So what we need are the equations that fit this. Well, the silver between 350 degrees and whatever the temperature of the water was when we started, let's see, 30 degrees C, silver is going to be a solid, okay? It would have to be up, I don't know what it is, but it's well over 1,000 degrees before silver melts, I think. So this is the equation you use whenever you're just changing temperature. Okay, remember we have a whole graph. We looked at the water when it went from frozen water all the way up to steam, right? And what happens when you keep adding heat. And there were 3 of these kinds of equations, right? But this is all about temperature change. When there's temperature change, but not a physical state change, not a change from solid to liquid or from gas to liquid or something, then this is the equation you're going to be using. So it's the same equation on the other side too, but this is for water. So the values here are different, but the equation is the same. And the delta T part is calculated by temperature final minus temperature initial for both sides. And so we just start plugging things in here. So we put this temperature final minus temperature initial into this beginning equation, and we plug it into here. This whole side over here is negative. So I plugged this equation into the negative Q, because it is Q, and I plugged T final minus T initial in for delta T, and that's what I get on this side. You get the same thing on the other side. So I just laid it out for you, okay? Now, if you're not good at this stuff, this is what you want to do. Before you start putting in numbers, make sure you got your equation laid out properly. And you just need to know that for a problem like this one, where you put in something in water that's in a perfectly insulated overall mini universe, that the temperature final for the silver is going to be the temperature final for the the water. It's going to reach an equilibrium, okay? We learned about equilibriums in a previous unit. So now we're just plugging in numbers. At this point, we're just plug and shut. We plugged in the numbers we have that go on this side. We don't know temperature final, so we have to leave that alone. We plug in what we know on the other side. And again, temperature final is unknown. Okay. Now we have to distribute. Okay. Now I don't know what grade you learned this, but probably somewhere around 5th grade. Learned about distribution of multiplication over addition or subtraction. So we're going to distribute. We're going to take the 20 grams times the 0.233 joules per gram per degree C times TF. We're going to multiply those three together, and then we're going to subtract from that this times the 350 degrees C. Okay? And the same thing on the other side. This number times this number times this number. Subtract here this number times this number times this number. Okay, when we do all that, this is what we get on the left-hand side. So we multiply this times this times this. That's what we have. This times, there it is. And then this times this is over here, and we subtract that second term. The same thing on the other side. This times this times this, and we get this. There it is right there. Minus this times this times this, and there that is. Okay? And again, if you're not good at this, don't skip this step. Lay it out so you can see what's going on, because this is the step where you want to cancel your units of measurement. Okay? If you don't show the units of measurement being canceled properly, you lose points. And it's also going to help you solve the problem because the dimensional analysis is going to work out. So we're going to cancel out all the units we can cancel out. Grams cancel here. Grams and degrees C cancels here. Grams are going to cancel here. Grams and degrees C cancel here. And now we can do some of the math and start to condense some of this. So if I multiply these three things together, I get this. I can't cancel joules. I can't cancel TF. I can't cancel degrees C, so that's all staying there. Over here, I cancel the grams and degrees C. I've got joules left. That's what I have here. And I'll do the same thing on the other side over here, okay? Get those numbers. Now, I want to get rid of this negative sign over here, so I'm going to multiply a -1 times this, and I'm going to get a negative term here and a positive term here, and so we've got all this ready to go. Now what we want to do is to start trying to get the TF by itself. Sometimes in math they call that collecting terms. Okay? To make that happen, then I need to do some math to both sides of the equation. You can't do it to one side of the equation. You got to do it to both. So what I'm going to do here is I'm going to subtract this term here from both sides. Okay? I'm taking this term here and I'm subtracting it over here, and I'm also subtracting it over here. Now, while I'm doing that, I'm also going to get rid of this term on this side to move it over here, because that's collecting terms. So I'm going to subtract this term from both sides, and that's what I get there. See what I'm doing? Yes? Now the result of that then is these two terms on the left cancel out, these two terms on the right cancel out, and I've collected terms. On the left, I've got the same units all together. On the right, I've got the same units all together. But by doing that now, I can do a different math where I can isolate the unknown. I'm getting ready to isolate the unknown. First, I want to get rid of these negative signs on both sides. Now, you may have set yours up so you don't have negatives. That's okay. If you started up here with silver being positive and water being negative, you won't have negative signs down here. But I've got to get rid of the negative, so I'll multiply both sides by -1. All right, so now we're here. Now we're ready to get TF all by itself. All I got to do is multiply by the inverse of this. Okay? And if I do it to the left side, got to do it to the right side, cancel out what I can cancel out, and there's our answer. Everybody see? All right, so that's a lot of math. But the math skills you have, it's just a lot of detail to keep up with. Okay? So, remember what your first grade teacher said? Neatness counts. All right? It's going to really matter that you keep everything neat and highly organized. All right, coolest thing. We have a texted in question for a student who can't be here today, and she wants to make sure we're covering everything that she needs. That's great. That's taking control of your own learning. I love it. That's fantastic. She wants to know about phase diagrams. Just wants to review phase diagrams. So when it comes to phase diagrams, there are really only two you need to know. Now, in reality, every substance has a different phase diagram. And all we're dealing with is solid, liquid, and gas phases, okay? In reality, there are lots of different solid phases. Seems to me water has about 5 different solid phases, okay? Depending on temperature and pressure and such. We're not going to get into that. We're only going to stick with the simple stuff. And what we're doing here is, with these general phase diagrams, we're like taking all the behaviors of all the substances and finding kind of a summary or middle ground or an average for all these things, okay? So we're going to be comparing. Now, in a phase diagram, there is no independent variable on the axes. In a phase diagram, the dependent variable, it's what's happening to the phases inside. We actually have 2 independent variables here, all right? So remember that with graphs, you've got a lot of graphs, and we do labs, we always have graphs. We've got an independent variable we put on the x-axis or the horizontal axis, a dependent variable we put on the y-axis or the vertical axis. But in reality, there are graphs where there is no true independent variable to graph like this. In this case, we've got 2 independent variables. So what's changing down here is pressure, right? Is it pressure down here? Temperature up here?
Yeah.
Make sure that's right. Let me think of it through.
The one on the practice test has temperature on the bottom.
Temperature on the bottom? Okay. So temperature down here. And since we're doing a general phase diagram, we don't have any temperature units down here because every substance has a different temperature set of temperature units. And so pressure is going to be up here or over here. And so pressure increases going this way, temperature increases going this way. Now, there is, for every substance, or every substance I know of, there's always a region where the pressure and temperature are low enough where the liquid phase cannot exist. Okay? So there's only solid and gaseous phase. Okay? So this region over here is where the solid form of these substances would be, and down here is where the gas phase of these substances would be. And if the pressure and temperature are low enough, you've always got this sublimation range. Sublimation is where solid goes straight to gas without going through the liquid phase. Okay? So sublimation is solid to gas. Gas going to solid, directly to solid, is called deposition. All right? So this is a sublimation deposition range here. All right? Now, for most substances, the boundary between a solid and a liquid leans a little bit to the right. It's a positive slope. Now, it's not a perfectly straight line because technically they're really, this actually can curve and this can curve too. We think of it as a straight line, okay, just to keep it simple, all right? And so there's a point here where we have solid, liquid, and gas all at the same time, and this is called the triple point. If we got the pressure and temperature balanced out just right, we can have all 3 physical states at the same time. Okay, that's right there. Now, again, we're making this as a general thing, so we're going to call this a curve that always has a positive slope, like this. All right, and this is our liquid region. Okay, so remember, independent variable. This is the dependent part. Okay. So notice this is a positive slope. It never dips down, and I don't know of any case where any of these would have any other kind of slope. You might have a curve, but this is always going to be a positive slope, positive slope, positive slope. Okay? But there's a point up here where the pressure and temperature reach a point where you cannot have a liquid anymore in its true sense. And so when that happens, you've got pressure and temperature so high, and particularly temperature so high, that you cannot have a liquid. This is called the critical point. And so when you get past this point, then you've got a special category called a critical fluid. And critical fluids are pretty important nowadays. For instance, if we're going to decaffeinate coffee or tea, we use, I'm sorry, that's not critical, supercritical fluid. If you're going to decaffeinate coffee or tea, are you going to use supercritical CO2? It does a good job of getting rid of the caffeine without getting rid of a lot of other things. Although Anybody who's a coffee connoisseur knows that decaffeinated coffee or tea don't have quite the flavor, because you actually do get rid of some of the flavoring and some of the odoriferous compounds as well. Those that give you the smell of coffee or tea. Okay? So that's a phase diagram, a general phase diagram. This is a general phase diagram for most substances. Everybody understand? The only difference between a phase diagram for most substances and the only specific substance that I'll require you to know about is this line right here for water. Okay? So for water, its phase diagram looks exactly the same, but this line leans back. It's a negative slope. Does that make sense? The reason is that water expands when it freezes. So now let's go back and talk about structural behavior, which was a couple of units ago when we're talking about structural, the structure of physical states, right? And we said that water, and we looked at, we took some little magnetized water molecules and put them together to see how they stick together, right? The thing that those magnetized models don't show you, though, is that when water molecules link together, they do so by hydrogen bonding. Hydrogen bonding requires water molecules to be a little bit further apart than they can be if they're twisted so they're not hydrogen bonding. So a water molecule that is not turned in the right angle and doesn't hydrogen bond can be closer together than one that does hydrogen bond. But of course, hydrogen bond is a much stronger attraction. So when it freezes, when water freezes, it freezes in that correct angle to make hydrogen bonding happen, but it makes it push apart a little bit. So the result is that water, when it freezes, actually separates just a little bit. And so water expands when it freezes. That's why we have potholes. And if you live in our state, where we don't have, we're fighting over highway funding right now in the state legislature and such. I see somebody nodding the head of yeah, I know that, okay. We have all these potholes that aren't getting filled because, you know, they're not putting the money into fixing highways, okay. And so the water falls down as rain, and then you get a really low temperature, and the water that's in the cracks and stuff freezes and pops little pieces of the pavement off, okay. It's also when we have landslides in the mountains. Okay, we don't live very far from the mountains, so the water gets down in the cracks in the sides of the mountains and breaks off the rocks, and it comes sliding down the hill. Okay, so that's kind of it's why water floats when it freezes. So when you put ice in your tea, we live in the South, we put ice in our tea, the ice floats on the top, right? Other places in the world they have iced coffee, and we drink iced coffee around here some now. You know, when I was your age, we didn't have iced coffee. We didn't know what that was. Nowadays, you can go to Starbucks and get iced coffee. So anyway, that's just sort of an application of this difference here and why it happens. Okay. So let's look at a different type of diagram. This could be called a phase diagram, but I call it a heating curve for water. And every substance has a heating curve, but water is used so ubiquitously, we usually use that as our example. And so what we're going to do is we're going to add heat to water down here on the x-axis. This is a true independent variable type of graph, okay, where heat is going to affect temperature, and that makes sense, doesn't it? Mm-hmm. Okay, and so as we keep adding heat, we're going to have these different regions. Okay, we're going to start out, well, in this right now, I'm showing where the steam goes, the heating or cooling steam. Then you've got a region where the water is condensing or is boiling. We've got a region where we're heating up water or cooling water. We've got a region where we're going to either freeze or melt ice, freeze water or melt ice, and then a region where we're cooling down or heating up ice, okay? And so our temperatures vary based on what's going on. If I have a sample of ice and I heat up and I add heat to that ice, the ice itself can only heat up to the point where it starts to melt. So the upper temperature range for ice is always 0 degrees C. It's not going to go any higher. Okay? And so while it's melting, there's no temperature change. Okay? Once it's completely melted and we've got liquid water, then we can start to heat up the water. All right. But now water, remember, can only be, well, unless you have supercooled or superheated. We won't get into what that means right now. Okay. It is possible to do that. But when you're heating up the water, you can't get the water any colder than 0 degrees C, because at 0 degrees C it starts to freeze. Or if you're heating it up, you can't get any hotter than 100 degrees, because after that it starts to boil. Okay? And so while it's boiling, it's staying at that 100-degree point. And it boils and boils and boils, and finally we get into steam. We can heat up the steam.
Okay, that makes sense.
Okay? And so we got all those different equations that fit in those different places. So here's that Q equals mass times specific heat times change in temperature we looked at earlier. It fits the ice region. But when we get to the phase change, we're melting the ice or we're freezing the water. That's a different equation because there's no temperature change. You can't have a temperature change there. We just use this enthalpy function here, okay? And that value is known, all right? And so all these different values fit in these different places to calculate it. So if I'm heating up a sample of water that's frozen, and I want to heat it up until it's into steam, and I want to heat it up to some temperature in steam, I've got to calculate this temperature range for the change in energy. I've got to calculate the change in energy while I'm melting it. I've got to calculate the temperature, the Q, or the heat, when I'm heating up the water. I've got to calculate the Q for boiling the water, and I've got to calculate whatever Q there is for heating up the steam beyond 100 degrees C, and then you add all of those together. Okay? So if we had a question like this, you see, we'll be adding heating ice, melting ice, heating the liquid water, boiling the water, and heating steam. So, and that's the equations we'll be using all those equations and adding them together. Does that make sense? So I was asked to go back to the beginning of the unit, where I think one of the first math type problems we did was calculating the energy produced in a combustion reaction. And so here is a problem of that type, and we've got how much heat, this is the question, how much heat will be produced from burning 150.0 grams of ethanol. And I have given you the heat of combustion is 1368 kilojoules per gram. That should be kilojoules per mole. It says that at the end. Let me fix that. How about that? That's pretty fast, huh? The heat of combustion is 1368 kilojoules per mole, and this means that delta H is equal to negative 1368 kilojoules per mole. I put that in there just to remind you of something that you kind of need to know, and that is that when we talk about heat of combustion, that is referring to what's happening in the surroundings. When we talk about delta H, the enthalpy, that's what's happening in the system. So remember that energy, if it leaves the system, the only place it can go is the surroundings. And so when the system is losing energy, the surroundings gain energy, and we feel the heat. We burn something, it feels hot, so we feel the heat. That's what we're writing it basically in two different ways. It means kind of the same thing, but you need to know about system and surroundings and how those are related. So let's just jump back for a second to the very beginning of this unit, and we're talking about system and surroundings, and sort of remind ourselves of what we're talking about here. So theoretically, the way that we think about these things happening is that whenever energy is going up in the system or going down the system, that energy is being transferred in or out and going out to or into the surroundings. The system is the part of the universe we're studying. It really doesn't matter a lot of the time whether you call, as in this case, well, in this case it matters, which one you call the system or surroundings, because we're talking about energy transfer here, okay? But when we're talking about combustion reactions like this, the system is the chemicals and the energy held in the bonds of those chemicals. And so when we burn those chemicals and that chemical reaction takes place, bonds are being broken and reformed, but overall the bonds at the end have less energy stored in them than the energy we had in the beginning. And so the enthalpy or energy stored inside the chemicals is less at the end than at the beginning. So one of the things we looked at in this unit was called a reaction energy diagram, where we looked at that and we talked about how energy is reduced, and you have to have an activation energy hill and such to you start out with more energy than you end up at the beginning. So the system then is what we're talking about here. We're talking about energy being lost by the system. That energy is being transferred to the surroundings, and the surroundings are the rest of the universe that interacts with the system. Now, a lot of the time we're doing math problems where we're sort of isolating a tiny little piece of the universe, completely insulating it from the rest of the universe. That's a calorimetry type problem. In a case like that, I like to talk about that being a mini universe separated from everything else. Altogether, system and surroundings make up the universe together. So let's go back to the problem now. How much heat will be produced from burning 150 grams of ethanol? When we burn that much ethanol, the heat stored in the bonds of the ethanol and the oxygen it's reacting with is being transferred out from the system to the surroundings, and it feels like heat to us. So heat of combustion, the heat of combustion number is the energy transferred to the surroundings. The delta H number is the system's energy, the energy change within the system, because the bonds are losing energy as we go from reactants to products. We are transferring that energy out to the surroundings. Okay, let's start looking at how we're going to solve this problem then. All right, the first thing to do is to figure out what the chemical formula for ethanol is. So let's review back many units ago where we were doing organic chemistry, learning how to name organic compounds. And eth, the prefix eth in organic naming systems, the nomenclature of organic compounds, eth means two carbons bonded in a chain. The OL, or ethanol, the OL means there's an OH group or an alcohol group on those two carbons. The AN in the middle of that word just means there's only single bonds between the carbon atoms. So there's only two electrons being shared between the two carbon atoms. So what we're going to have then is this structural formula. This is a complete structural formula. There is a single bond right here between these two carbons. That line right there represents the two electrons that are being shared. There's an OH group on one of the carbons, and then each carbon has to have 4 bonds. So whatever additional bonds a carbon needs, we fill it out with hydrogens, okay? And so we get this formula, and that's CH3 in this group here, CH2 in this group here, and OH on the end. And then we can write this condensed structural formula here from that. And this is a skeletal formula for the same compound. The skeletal formulas, I won't go into too much detail. It's a review. Show only the bonds between carbons and any functional groups like this OH group. So this corner here would be a carbon, and this end over here would be a carbon. So sometimes we talk about skeletal structural formulas showing carbons at ends and bends. All right, so our formula is CH3CH2OH, and what we need to do is to balance the equation. If it's burning, and we're saying burning ethanol, then ethanol is reacting with oxygen. What we need to do is to balance the equation. And so using the atom inventory process, I figured out there are, in a balanced equation, there are 2 ethanols, 7 oxygens, 4 carbon dioxides, and 6 waters. The products of a combustion reaction with a hydrocarbon fuel like this is always carbon dioxide and water. Assuming it goes to completion, we are assuming it goes to completion. So this is the way we balance equations. You have to use this atom inventory process in my class. And to make the equation, though, fit our combustion system, our typical combustion equation, and fit that delta H value, that 1368 kilojoules, it should be per mole, and here I've got it per grams again. Let's just ignore that. You know it's per mole over here. Actually, I changed it there, but I didn't change it in the previous slide, did I? I mean, I've changed it down here, but not there. It should be kilojoules per mole. We need to change this equation so that we've got a coefficient of 1 here in front of the ethanol, because the amount of energy is kilojoules per single mole. So that refers back to our fuel. We need a single mole of this. And those coefficients can represent single molecular units or moles of those units. And so we want to divide, in this case, all the coefficients by 2 in order to get a coefficient of 1 in front of the ethanol. And so it looks like this. So now we've got 1 mole here, 7/2 of a mole for oxygen, 2 for carbon dioxide, 3 for water. This is the only kind of equation where you are allowed, at least at this level in chemistry, to write fractional coefficients for a balanced equation. But it's set up to show that this much energy is lost by the system here. Delta H is what's happening in the system. It's the change in heat energy stored in the system at constant pressure for 1 mole. And this equation then fits that number. So what we want to do now is to find out if I have 150 grams of ethanol, how much energy is produced. Since our energy is not listed in grams or kilojoules per gram, it's listed in kilojoules per mole, we've got to convert this 150 grams of ethanol into moles. And so we're going to have to calculate molar mass. And this is the way we do it in my class. Calculate molar mass like this. We end up with 46.07 grams of ethanol is equal to a mole of ethanol. We're going to put the starting amount of 150 grams of ethanol on the top of a 1, making a fraction out of it here, and use this equality statement here to justify and build this conversion unit. This conversion unit is called a unit because it equals 1. What's on the top is equal to what's on the bottom, so that fraction is equal to the number 1, and it's called a unit. And then this is also a unit. This is actually stoichiometry, because what we're doing is including this math, this value here in the equation. We could put on the end of this plus the positive 1368 kilojoules and actually make it part of the equation. That's what we did when we first started learning about this. And so it really is part of the stoichiometry. And so now we're going to calculate our answer to find out how much energy is produced. We get this number here on the calculator, and then I'm going to find the significant digits and round off properly. There are 4 significant digits in this measured number, 4 significant digits in this calculated number, 4 significant digits in this calculated or measured number. It is calculated, but it's also measured to a degree too. And so all the measured and calculated numbers, we've got 4 significant digits. Those are the least digits in the problem, and that's how we're going to figure out how many digits to put in our final answer, 4 digits. And that's the answer. That's how we figure out how much energy is produced from burning 150 grams of ethanol.